We need to define a Hamiltonian operator in terms of a kinetic energy operator and the potential. We're going to set up the problem the same way we did for the particle on a sphere problem. So that is the same equation we have there, and we can use what we learned from the particle on a sphere problem. Angular term, those YLMs, the spherical harmonics, we already found the solution from the particle on a sphere problem, right? And we're going to use that same solution here. But now we want to turn to this radial equation, right? We need to solve the radial equation. And how are we going to do that? Well, we look back at the equation that we had before. It's a second order differential equation. And so how do we solve a second order differential equation? Wait for it, we ask a Belgian monk. What, you may ask, do we know about Belgian monks? Well, first, they were from Belgium. Second, they could only drink 3 pints of beer a day. And third, they wore burlap underwear.
Burlap?
Now, if you were from Belgium, could only drink 3 pints of beer a day, and had to wear burlap underwear, what would you do? Well, solve second order differential equations, of course. Right? We need to look back on what has been done and use somebody else's solution. And we know that the Belgian monks have been doing this, right? We know the names associated with a lot of the functions we're going to use and other properties, right? Laguerre and Hermite, they were, of course, right from near Belgium there. Laplace, Legendre, Lagrange. All right, these places might not be all that close to Belgium, but they were all in Napoleonic times. During Napoleonic times, both Belgium and Italy were part of the French Empire. And therefore, that they must have had a holiday in Belgium. So I think they all qualify as Belgian monks. Now, you might say, yeah, but what about Hamilton and Schrödinger? They weren't Belgium. They weren't even close to Belgium, right? Nowhere near. Probably didn't holiday there either, right? But note, they didn't come up with the solutions to second order differential equations. They used the solutions of the Belgian monks to solve their second order differential equations. So now that's exactly what we have to do. We have to meld this into the form of a known solution, and then we can use those solutions in our problem here. And indeed, we'll find that the solution looks like an exponential function, an exponential times, wait for it, a Laguerre polynomial. We're going to have three quantum numbers, n, the principal quantum number, L, the orbital angular momentum quantum number, and m sub L, its projection. In the hydrogen atom, the energy to a first approximation only depends on n. So now the form of this overall variable separated wave function makes a whole lot of sense. We introduce radial nodes and control the energy largely with the radial term, but the shape is determined by these YLMs. We now have solutions for the wave functions. We take those wave functions, we substitute them back into the Schrödinger equation, and we'll determine the energy. We solve for the energy then. And the energy we find in the Schrödinger equation only depends on n. In one electron system, to first approximation, the energy of the levels only depends on n. All s, p, d, f orbitals of the same value of n, they're all degenerate.